Hello, in this video we're going to try to understand the rule of 72. And being a math and statistics channel, we're going to try to understand it from a math and statistics perspective. Now, I reviewed maybe a half dozen or more YouTube videos on the rule of 72, and every one of them have an impressive display of how to use the rule of 72, why it's important, why we should continue to use the rule of 72, but none of them describe this rule mathematically. And so that's the twist that we're going to do using this video. So the goal of the rule of 72 is how long before our investment doubles. And the rule is quite simple. The number 72 is divided by the interest rate to obtain an approximate number of periods required for the investment to double. And the formula is this: T equals 72 divided by the interest rate. And T would be the number of periods that it takes to double. Now, a note on this formula that, why is this so easy to use mathematically? And one of the reasons is 72 has several divisors. One divides it 2, 3, 4, 6, 8, 9, 12. They all divide 72, which makes mental math so much easier when you have numbers that divide into it. Now, one of the super important reasons for the 72 over the interest rate is that the rule was likely developed in the 1400s. There's proof that it was way, way earlier. Now, a lot of the videos say that Einstein popularized it, which may be true. I don't know that. But it was first used in the 1400s, and they didn't have computers. And so having a number like 72 with so many divisors of a typical interest rate, that it made this approximation so useful. Now here's a quick example. Let's invest $100 with compound interest at 9% per year. Then approximately T equals 72 divided by 9 equals 8 years. The investment will be worth $200. Now, the actual time is this: log 2 divided by log of 1 plus r, and it's 8.04 years. And so, calculating the log, you can't really do that in your mental math. But this is easy, and 9 divides 72, so it makes it even easier. In most of the videos here, they say use log base 10 for both of these, and in here my natural inclination is to use the natural logarithm, and you can mathematically show that if you use log base 10 or the natural logarithm, or actually any log with base b, this calculation is the same. Mathematically, they're 100% equivalent. Now, in order to understand this formula here, the rule of 72, we have to develop some background before we just jump right into it. And very quickly, calculating interest is, we have some principal balance, we have an interest rate, and now remember, interest rates are between 0 and 1. So a lot of people convert that to percent though. So like if we have a 9% interest rate, that really means the interest rate is 0.09, right? But then we move the decimal twice and call it percent. But in all these calculations, we have to have it between 0 and 1. T is the time period. Now we set it to 1, which means, 1 could be 6 months, or it could be 12 months, could be 1 year. It's whatever that time period that the interest rate is compounded over. So the formula is I is equal to PRT, and that's the balance, principal balance, the interest rate, and the time that it's, that it compounds. So for example, for T equals 1, the interest, and from the example above, we've invested $100 at 9% interest rate, so it's 0.09, in one time period, so we've made $9 over that year. Now, compound interest and future value let's see how that's calculated. And as a reminder, t equals 1 is this. So we have our principal balance plus whatever interest we made. Remember, the formula is PRT, but we're looking at it over one period, right? So this is our future value after one period. Now, if we left factor out a P here, then we're left with P times 1 plus R, right? Because if you multiply that back in, you get this. Multiply that back in, you get this one. Now let's look at it for time 2. Now, once we've already gone through time 1, we just take, our new balance, our new principal balance, and bring it down. And then we calculate the interest rate on this new balance, which is P, our balance, times the interest rate. And it's only the interest over one period, so the T is a 1. Now here, we can left factor out a P and a 1 plus R, and that's what this represents. And then what's left over here is a 1, and we have an extra R. But here we have 1 plus R squared. So this is the formula from 2 periods. And you can continue to do this up to n periods, for some number. And your future value is P, your principal balance, times 1 plus R raised to the nth power. And that's your future value, okay? So now how do you calculate how long it takes to double our balance, our principal balance to double? So if this is our future value at some n, which is what this is, we want it to equal twice our principal balance. So you set this formula equal these two values, and we solve for n. We're trying to find the time period that our future value equals twice our principal balance. So we divide both sides by P to get rid of the P, and that's what we get here. Now if we take the logarithm of both sides, we get the log of 2, and then we get the logarithm of this, but the log of it, that's exponentiated can come out front. That's what this, so it's a property of the logarithm. Then we divide by log of 1 minus R to the other side, and we get this formula. N is equal to the log of 2 divided by the log of 1 plus R. Now here I used natural logarithm, but in all the videos actually it said use base 10. But mathematically, this is 100% equivalent no matter what base logarithm you use. So this is it. This is the exact. And me personally, we all have scientific calculators in our pocket, with our cell phones. So calculating this exact value is so easy nowadays. Log of 2, divided by the log of, say 1.08 or 1.09 or whatever your interest rate is. And that's so easy to calculate, and it's exact. But here we're trying to understand the rule of 72. Now, one way to think about this rule is this, that we're going to think about an average interest rate could be 8. So for typical values, say from 1 to 16, the middle would be 8. And if we take our exact calculation and kind of separate it into 3, so we have the log of 2 here and the log of 1 plus R, and then this R cancels with this R, so we get this back. But let's look at this right here and plug in, say, the average R to there and here, and we crunch that number. We get 72.05, right? And now remember, this is a number between 0 and 1. So we multiply the top and the bottom by 100 and truncate off this 0.05. And that's where we get 72 divided by our interest rate. And that's it. That's the rule of 72, and that's how it was developed. Now, it, to me, is so surprisingly accurate that it's pretty amazing how simple it is and how accurate. Now, since the 1400s, so many more rules of thumb have come out, and now we have, You know, the rule of 69.3, the rule of 78, the rule of 72. I mean, this one ends up being the most accurate over the entire spectrum. At least I think so. Well, of course, this is the most accurate, the exact. Now, another common one is the rule of 69.3. And remember this, and this was developed in the era of, we have basic calculators, you know, and when basic calculators became, you know, just ubiquitous, then this rule was very important, especially with little interest rates. And I want to give a little intuition of this, and then we'll end the video. And the rule of 69.3 is more accurate when we have little interest rates. So say less than or equal to 5%. Then this rule is more accurate than this. This one's still surprisingly accurate. And for values greater than 6, this is more accurate. But you take the exact calculation, right? And the log of 2 is carried over. And then when the interest rates are small, this log of 1 plus r is actually really close to just r. And the log of 2 is 0.693 da 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 da. So you multiply top and bottom by 100, and then you get this. So this is the rule of 69.3. And one little note here, why this is so accurate to this is this little graph. So we have an x and y coordinate system, and we have the logarithm function come up like this, and then we have the straight line y equals x here. Now notice that when we're really small here, those two functions, those two lines are almost on top of each other. And that's why when x is small, you can just substitute in r for log of 1 plus r. And that's how they developed the 69.3 rule. But to keep the video at a good length, we better end it. And my just closing comment is that the rule of 72 is pretty close for all cases. And just the ease at which it is to use, I think it will probably be used for quite some time. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.